Hello? Wait. I need to. Can you hear me? Yes. Hold on. Wait. Okay, what about now? Testing. Yes. Good afternoon. What's up? How you doing? It's been so long, right? It's been like, what, couple hours? Okay, so I'm going to ask you for forgiveness again because I need to set a couple things up here on my end. So which is going to be this and this. Am I here? Am I here? Okay, I can see that. Sorry, I'm trying to connect my other computer to the stream. Good afternoon, Chandra. How are you doing? Good to see you. And we're gonna connect to. There you go. There you go. Exactly. Very good. And now, just going to put this here and put this here. Oh, I'm out of coffee. What are we doing now? And then this is going to go here, I guess. And this can go here. Okay, where were we today? We were. Ooh, let me stop. Wait, like I have to finish setting a couple things up. Yes. Here and here. So that's one thing. What else do we have? Afternoon coffee, exactly. That's what we're doing, Chandra. Let me actually go get my coffee. I'll be right back. Hold on. Okay, I am back. Woohoo! Oh, what a late afternoon. Okay. Am I ready for this? Are you folks ready for this? Hmm. I guess. I guess. Okay. Uh, what the hell? Okay, sorry, I got a text message. That was very funny. Okay, are we ready for this? All right. 1, 2, 3. Good afternoon, everyone. This is Parametric Camp. My name is Jose Luis. I do it. Should I do this every time? Yes. So we are Parametric Camp. We do computational design live streams. We record tutorials live in the company of all this beautiful community, like you folks that join me in these afternoons where we talk about computation. We learn how to code. We learn how to apply all these techniques to creative endeavors. So, as you may or may not already know, if you are new to this channel, so you're very welcome. Please consider, if you like what you see today, please consider liking this video, subscribing to the channel, hitting on notifications so that you get messages and pop-ups and emails when we go live. Otherwise, you are welcome to subscribe to our social media where we announce when we're going to be doing stuff. And I'm also going to post here a link to our Discord server where we have offline conversations throughout the week. We have a channel called Introductions where people can introduce themselves and say hi, who they are, why they like computational design, etc., etc. And we also, if you want to know which events are coming up, we have a Google Calendar that I'm posting here in the chat that you can subscribe to get the events for when do we go live. What we're doing this week is that we typically do live streams on Fridays, but I have this playlist, this series on introduction to parametric modeling that I want to wrap up. So I decided to do a live stream hackathon or live stream thon or whatever you call it this week. And so I'm going to be doing live streams every day twice until we wrap this playlist up, which I'm very excited about. So now, what are we doing this afternoon? So this morning, we went through, what did we do this morning? We discussed what Nernst geometry was. We discussed what Nernst geometry was. We saw how to create basic Nernst entities in Rhino. That's what we did this morning. And then I also created an exercise in Grasshopper to do lines, polylines, and splines. So that was this morning. And the exercise looked something like this. So I think what could be super interesting today now is to discuss what do we have on the back burner. So how to import Rhino geometry into Grasshopper. So that could be super. Oh, wait. So that could be super interesting. And then how to do surfaces. I think I have a file somewhere that I may want to use just to import stuff. And I think that's what we're going to do. Is this what I want to do? Is this what I want to do? Is this what we're doing? Yes. Okay, so what we're going to do is I'm going to take this file and then I'm going to take each one of the 4 points and I'm going to import them independently. That's going to be one thing. The other thing we're going to do is The other thing we're going to do is we're going to import a list of polylines and a list of points and just place a bunch of spheres on top of them. Create two curves, and then we're also going to take a couple curves and loft them, for example. That could be interesting as well. Okay. Okay, I think we're going to do that. And I'm going to save this without this, and then I'm going to save this. Importing Rhino geometry. And then I'm going to place this thing again. The bifocals for 2. Okay. All right, so let's do this. Am I ready for this? Also, I think my batteries are, you know what? I'm going to change the batteries right now because I hate it when I'm half through the stream and then the batteries die and then I have to repeat the thing and it's just not great. So I'm just going to. Can you hear me? Yes. Yoo-hoo. All right. Okay, so let's do this. So that's going to be 4.4. Going to be 4.5. Okay. All right. Hi, this is Jose Luis and welcome to a new video on this series on Introduction to Parametric Modeling, where I'm going to teach you how to import geometry from the 3D modeling environment into the parametric modeling environment so that we can work with geometry as a source of information. But let me frame this, why is this important in the first place? So in the example that we did on the previous video, we saw how we could create, for example, 4 fully parametric points in 3-dimensional space by controlling the x, y, z of each one of those points, and then create then polylines, create nerves curves or interpolated curves between those 4 points in a full parametric way, right? However, turns out that sometimes, for example, working with pure parametric information that has been generated numerically is not very convenient. First of all, because, well, maybe these points, the way I'm working with them right now, I can control the XYZ, but sometimes controlling the XYZ is actually not very intuitive. Sometimes we want the fluidity or the interactivity that just dragging here on the viewport, like dragging the points and moving them with the mouse, moving them up and down, it gives us a bit more flexibility and fluidity when we are modeling things. So maybe instead of working from 4 points that we have defined numerically, maybe we want to work from 4 points that we have defined in the 3-dimensional environment in Rhino. Or, for example, let's say that we're working on a definition that does some parametric magic, but it needs to start from some actual data, graphical data that our client has given us, that the site has given us that it's part of what exists in the real world. And that data may come in as CAD information, may come in as a file that you load into Rhino, and that is the data that you want to bring in into your parametric definition. Replicating all the data that you may have on a CAD file numerically here could be really tedious, especially if you're working, for example, with thousands of input points. It's just not practical. So at that point, what you want to do is you want to bring in geometry, actual geometry from the modeling environment to work as input information in your parametric modeling environment, which is what we're going to do today. So what we're going to do today is that I'm going to replace these 4 points. I'm going to completely ditch them from my definition. And what I would like to do is I would like to create 4 points that are going to exist here physically in Rhino. And when I mean physically, I mean digitally actually, but in the 3D modeling environment, right? And 3 points that I can actively manipulate and move around with the Rhino interface. And then what I'm going to do is I would like to work with this, with the XYZ and the XYZ of this as information that comes as input in Grasshopper. So the way I'm going to do that is, in the case of Grasshopper in particular, we do this by using input box parameters. What does that mean? If you go to the parameters tab, and if you go, for example, to geometry or to primitive, what you will see is all these icons that we have seen previously here when we hover over the inputs of any component. So for example, this is a point, this is an integer, this is a Boolean, and we can see that by saying this is an integer, this is a Boolean, this is a point. But if I actually use this, if I actually click on point and I drag this into the Grasshopper canvas, what I will get is this empty box, an empty component that can store or transform or manipulate point information. What does that mean? Well, this means that these boxes are designed to contain collections of whichever type that component is indicating us. So in the example here, in the example of point, this box can contain this component can contain points. So what I'm going to do is I'm going to right click on this component, and I'm going to set here on the options that I want to set 1 point. As I do that, Grasshopper closes temporarily, and then I can select this first point here. And now you can see that the component went from yellow, which was a warning, to a full gray. And now if you click here, you can see that this component actually contains information from a reference point in Rhino. And you can see here, if we zoom in, that there's already a pre-visualization in red. If I click here, this goes green, meaning this point is contained here. And what's nice about this is that if I make any changes to the point in Rhino, those changes will be live linked to the box that I have here in Grasshopper. So I'm just going to drop 3 more of these, all right? And I'm going to line them up nicely, whatever. I'm going to right click, set 1 point here. Now's the second one. Now here is going to be the third one. And now here is going to be the fourth one. And now I just have 4 points that are linked to the physical points here in Rhino. And again, I say physical, I mean digital in the model here. And that I can use as 3-dimensional points for any operation in my Grasshopper definition. So for example, I'm going to plug in here the 4 points to create a polyline. I'm going to plug in here the 4 points to create a Nerves curve. And I'm going to plug in here the 4 points to create a Interpolated curve. Okay, awesome. How great is that? So these boxes, these empty parameter components, what they're very useful for is to load information from Rhino and to use them as input information in Grasshopper. But I just want to let you know that these parameters, all of these, in general, they're basically empty containers that can hold information either by manually loading it from Rhino or by just passing it through. So for example, you saw how in order to get these 4 points, I had to here in the polyline in the nerves, I had to like go over one of each, one at a time, etc., etc. An easier way would have been to say, well, I loaded the 4 points independently, but then what I'm going to do is I'm going to plug all of them together into another empty box. So instead of manually loading now, what I do is I connect this one here and I have the first point. I add the second one with a shift. Now I have 2 points coming out of this component. Now I'm going to add the third one with the shift. I have 3 points and the fourth one with the shift, and I have 4 points. This container here, this component is now storing a collection, is storing 4 points inside of it. And you can notice how the continuous single line thread wire has changed to a double while, meaning that instead of 1 unit of data, now we have a list of data passing through this wire. And with 4 points here, now it's much easier to say, well, now I can connect this to the polyline, to the nerves curves, and to the interpolated curve, and things are a little easier to handle. So from 4 points, I have just connected to 1 point, to one list, and then that list is the list that I plug into my inputs for the geometry. That could be another way to go. A third way to go could be, well, if I know that these 4 points are always going to be the same and in that order, I can just skip all of that directly and then drop an empty box, right click and set multiple points. And then what I can do is I can say clicking in order, and the order here is very important, first one, the second one, the third one, and the fourth one. This blue line is a pre-visualization of the order. And as I right click, then the 4 points are now stored in this container, and I can plug them in here, plug them in here, plug them in here. So now I have a list, I have a component that contains a list of 4 reference points that are coming in from Rhino. And again, the beauty of this is that these 4 points still exist in Rhino, but they are linked dynamically to Grasshopper. So if I modify any of the points in Rhino, that point will be modified here on the list, and then those changes will broadcast to how I generate the curves inside of Grasshopper. Okay, so this is a really good way if you want to create like a modeling environment that allows you some hand manipulation, but at the same time it has all this parametric logic in the back end, or if you just have to work with data that somebody has given you somehow on a CAD file. All right, so let's for example take a look at other examples of things that we can do by bringing in data as inputs into a Grasshopper definition. Oops, let me save this file. It's going to be 4.4. Okay, and then I'm going to move here. Hey Josh, how you doing? All right, so I'm going to create a bunch of points here. For example, I have just moved away. I have turned off pre-visualization of here, and I have moved away a little bit of where I was, and I'm just going to create a bunch of points, like a few of them. All right, so for example, like several, I don't know, 10 of them. I'm just clicking right click and left click, and then I create a bunch of them, and then I can create an empty point component parameter, right click, set multiple points, and just select all of these. What you can see is due to the nature of how I have selected them, they turn out to be ordered in this sequence inside of Grasshopper. But now I have here a list of 16 different points. Now with this, I can do whatever I want. I can, for example, Again, I can create a polyline, for example, between them, and then it creates that object there. I can create a NURBS curve from all of these points, all right? And then it creates this kind of fun squiggly line between them. That's kind of cool, right? I like this, actually. Or I can create an interpolated curve. This is a very common operation because very often we want to go through the points. So I'm going to create an interpolated curve. I'm going to turn off the other one and this other one. And you can see we also get a fun kind of interpolated curve. And again, if I modify any of the input parameters, any of the input points, everything adapts accordingly. All right. Or something that I can also do is I can use these points as centers for primitive surfaces. So for example, if I go to surface, primitives, and I go to sphere, and I place a sphere here, if I plug the point into the center of the sphere, you can see that each one of the spheres now is centered around each one of the points. Because the sphere, when it's given a list of data, it just applies the same operation to all the elements on that list. Further down in this list of tutorials, I will teach you how Grasshopper works with data and how can we manipulate streams of data. So that's another point. Or for example, if instead of points, we are tired of points and we want to do something different, something that we can do as well is we can use curves as inputs. So for example, let me say that I'm going to create this curve right here. And then I'm going to move over here and I'm going to double click and type on curve, which is, because of the hexagon icon, this is an empty parameter component that can contain curves. If I right click here and I set one curve and I click it, now this curve has been referenced in my Grasshopper definition. I have a referenced planar curve. And for example, I can create another one here, and which I can, for example, move a little bit in the Z direction. I'm going to bring that one in as well. So for example, curve, right click, set one curve, and I'm going to bring it in. So now that I have these two curves, things that I can do is, for example, I can generate a surface that is a loft between these two curves. So for example, I can go to surfaces, freeform, and I can find a loft component. This creates a lofted surface through a set of series components, of curve components. So for example, now I can plug my first one here, and then if I plug the second one with the shift so that it adds in both, you can see that I have a surface that is lofted between the two curves. And if I now change any of the curves, so for example, if I move it, the surface adapts. Or if I change any of the control points, so for example, I drag that around, the surface adapts to those changes. You see? And as soon as I get, by playing around with the two curves, as soon as I get the exact right surface that I like with the smooth surface, whatever, I can just right click, bake the object, and then I will have a copy, I will have a static copy of that surface that I can now send to other programs for rendering, for 3D printing or whatever. And remember, as per our previous videos, remember that if I still choose the curve and I move it around, the curve has lost the relation, the surface has lost the relation, the one in Grasshopper has lost the relation to the one in Rhino, because the Rhino one is just an imprint, it's like a footprint, it's like a stamp of when that surface, when we baked it. Okay? Wonderful. So this is bringing data into Grasshopper as an input. We will do that a lot in the examples that we're going to see very soon. Okay? So actually, I think at this point, right now, we know enough so that we can work on a few examples just to practice things out. Okay? So see you on the next video where we're going to do some practice exercises to get stronger on everything that we have learned so far. Okay? And remember, if you like what you saw, please consider subscribing, liking this video, turning on notifications, and all of that stuff. Thanks a lot. See you in the next video. All right. Hey, no, what's up? How you doing, sir? Um, am I going to lose audio? I'm probably going to lose audio, right? So hold on. Let me change. Hello? Can you hear me now? Yes. All right. Cool. So what is, oh, pipeline. I barely use that component. What is pipeline? Geometry pipeline. Oh, I have never used that. Defines a geometry pipeline. Rhino name, layer filter, name filter, include like hidden points. Okay. All right. This is cool. I've actually never used that component, I think. No. All right. Where are we going now? Okay. Ooh, all right. So I actually already did some examples. Oh, look, we're live. Yoo-hoo! Okay, so we did some examples, playlists, algorithmic modeling challenges. Yes. We did the pearl necklace. So, so actually, so my idea was to insert the algorithmic modeling examples, but I wonder if we should just do. I wonder if. Huh. So my idea was, we have the playlist, and I'm open to suggestions here. I think we have a playlist. The playlist is. So in the playlist we have blah 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 and blah blah blah, and we're learning blah, blah, and I just wanted to insert here as exercises. I wanted to insert the algorithmic modeling challenges, and I wanted to create. So I wanted to have. Yeah, I don't think that's gonna work because these are a little. My idea was to have the content for the course, and then as part of the exercises, instead of doing exercises just for the sake of this course, do exercises that were in general algorithmic modeling examples, and then bring those here and insert them here. But they were just in general algorithmic modeling challenge. However, and that's what I did. That's why I did the pearl necklace here. But now that I'm thinking about it, if I do that, it's going to be weird because maybe what I say here, which might be more generic, is not the same that I can say here, which is that I'm coming from a story that I'm trying to tell in the course. So that's going to be different. And also these ones are done typically in like several stages. I typically do just Grasshopper, playing Grasshopper, and then I typically expand to C sharp. So So I don't know. I think I may have to take that back. I may just not do. So what do you think? Should I do exercises that are just for the playlist? Or should I do exercises that are algorithmic modeling in general, exercises, and then they go here on the list wherever they should go? I'm not sure about any of this anymore. Hmm. I think I'm just going to record the exercises for the playlist and forget about, because honestly there's going to be many more people watching this and I would rather get the story right. I'd rather get the story right and not mess with I'd rather get the story right and not mess with what people know or they don't know, and not make assumptions. And also the recommendations at the end of the by the end of the video will be different depending on where it lives and which playlist it lives, which makes things a little messy. So, and also I may just not do C# implementations for these ones, because also if I do that, recording this whole thing is going to take forever. So yeah, so maybe I'm not going to do that. Okay, all right, decision. I will be recording exercises just for the sake of this playlist. Okay, so that is a decision that is just done. Okay, I may regret that, but I think that's a good thing to do right now. Yeah, let's do that. So I'm just going to save this. It's going to save this. I'm going to create a new one. And then I'm going to save this with that component and close it up. uh, So okay. All right. Well, we don't need to show an image of that. People can understand that. I don't think we need to show an image of that. Okay. And then for this one, am I going to start the exercises by the end? So am I going to start by showing the end of what we're doing? Or am I going to start wow, this is more difficult than I thought. Okay, well, before this gets too boring, I'm going to start drawing stuff, at least diagrams, so that we can explain, uh, so that we can explain. So we're going to start with a curve like this, and then the next thing that we're going to do is we're going to divide, and we're going to say that the 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 input parameters is going to be the number of pearls. Actually, probably I can draw that. And then, so in this one, in this next layer, I'm going to say, well, I'm going to divide that in the amount of and then I'm going to find the distance between them. Okay, so I'm going to start by talking. All right, and I think in the previous video I already explained. Okay. Okay, so I'm going to record a quick video, a computational design live stream. I may want to do one that it's, did I do one that was, did I do a backdrop that was intro to parametric modeling? Do I have that? Oh my God. Sorry, I should have prepared this a little better. Oh yeah, I do have one. That is Introduction to Parametric Modeling. Okay. No? Hi. Yes. Okay, so I'm going to use that backdrop then. Here, welcome to learn, blah, blah, blah. And then I'm going to just here. Oh God. Okay, no, that's not the one. Okay, so I'm just going to, okay, and then another one. This is going to be what? Image. Nope. And then I'm going to name. Okay. So, okay. So I'm just going to record a quick video saying intro to exercises. Hi, this is Jose Luis, and if you are on this video, it means that you have reached a point on our series, Introduction to Parametric Modeling, where you have learned a lot of the basics of how to create parametrically geometry in three-dimensional form. Starting over again. Starting over. Hi, this is Jose Luis, and if you're watching this video, it means that you have been watching through our series, Introduction to Parametric Modeling, and you have reached the point where you have learned a lot of the basics of how to manipulate simple geometry and how to create parametric relationships between the operations that you can do to generate three-dimensional form. So I think at this point, it would be interesting to take a quick break and then to do a few exercises to practice and to solidify some of the techniques that we have seen in the previous videos. If you feel you want to take that dip, I think will be super beneficial. And maybe through doing these exercises, we also learn a few other techniques that we haven't seen yet. But if you think you are very comfortable with everything you've seen before, maybe you feel welcome to just skip ahead over these exercises and just move on to to the next section where we start seeing more in-depth starting over again. I need to drink less coffee before doing these things. Hi, this is Jose Luis, and if you're watching this video, it probably means that you are already at starting over again. Hi, this is Jose Luis, and if you're watching this video, it probably means you have been following our series, Introduction to Parametric Modeling. And if you're watching this video, it probably means also that you have already seen a lot of the basic components and the basic techniques that we use to generate form in 3 dimensions in a parametric way with simple algorithms. And at this point, I think it will be beneficial for us to take a small break from learning new things and then put everything that we have learned to practice so that we can see how it actually applies in the real world for simple exercises, and then we can get a little stronger in those techniques. Also, maybe by practicing these, we may also tap upon a couple of other topics that we haven't seen yet. So we may also learn a little bit more, but I think it's very useful to solidify these concepts with a few practical exercises, so hands-on exercises. So that's what we're going to do right now. You're going to see in the next videos, you're going to see a bunch of exercises, very simple things, modeling a vase, modeling a pawn, modeling a chess board. So that should be very helpful for you. And also you will learn about many new components that we have not seen in the previous exercises, in the previous videos. If you, however, feel very comfortable with what you've seen before, you're welcome to skip ahead to the videos where we start going back to new content and data structures and more complex relationships. But I really suggest that you try to follow these exercises, even if it's just watching them and maybe like fast forwarding through them at like 2 times the speed. I don't know. I don't know how fast I speak. I don't know how boring I am, but it's totally up to you. Okay, so let's get hands-on and practice what we've seen so far with a few simple exercises. Okay, follow me on the next video. All right, that was good. So we're going to go back to parametric camp, yes, and then we're going to back here, and then we are going to create. I think I'm going to do as usual. I think I'm going to just start recording the video, doing the exercise, and then I will record a small clip by the end saying like, hey, welcome, this is Jose Luis, and in this video we're going to do so and so. And then show the thing working. All right? I think that's what we're going to do because I think it's just nice. All right? And I'm out of coffee. So yes, we should be good. Nylon. Nylon. Okie dokie. All right. So what are we going to start here? We're going to start with drawings. Okay. So this video is going to be about doing a pearl necklace, which is actually an exercise we already did, but I don't want to delete that other video. So we're just going to do it here again. Wonderful. So let's get started. This is the first exercise we do in the series. So it is a really, really good moment to step down for a second and maybe give you some advice on how I think problems that are about parametric modeling should be approached. And to me, personally, what it helps a lot before getting into any coding or any visual programming or whatever is to actually sit down and think through the problem, both conceptually and both perhaps geometrically, if you will, and then try to set myself a plan about how I plan to tackle the problem. Whether if I end up doing it or not, sometimes depends on my expertise, whether if I know the tool well or not, but at least sitting down and thinking ahead a little bit, I think is always very beneficial. So today in this exercise, we're going to do a pearl necklace. And a pearl necklace, if you think about it, is basically some kind of geometry in the form of a curve, which is typically the thread. And then it's a bunch of spheres that are placed on top of that thread with their centers on that thread. So if we are to break down the problem, we can think, well, probably the first thing that I want to think is that one of my inputs, one of the data that I'm going to have as that to work with is going to be the shape of the thread. Okay, let's imagine that this exercise is for some kind of visualization exercise, right? So I may have as input, as data that someone has given me, the curve of the thread. And then perhaps some data that is also parametric, so this could change, but it's an input. But some data that could also be useful for me would be to know, for example, the amount of pearls that my necklace is going to have. So I'm going to call that N, and that's going to be also an input. How many pearls my necklace is going to have. I may also want to think like, well, maybe the radius of those pearls could be an input as well, how big they are. But it turns out that if you think carefully about the problem and you assume that you have the thread and that you have how many pearls you want to put on that thread, it turns out that you cannot, if you assume that they're all touching each other, next to each other, it turns out that you don't have freedom to choose the radius, because if you have the thread and you have the number of pearls and they have to touch each other, then there's only one possible radius to satisfy that scenario. And actually, it's not exactly like this, but if we are to oversimplify this problem, the radius is not a parameter that we can freely choose. The radius would be the result of taking the total length of the chord. We're going to call that L, and we know that because we do have that curve and we can find that numerically very easy, divided by the amount of pearls. All right, more or less. Now is this how I want to do this? Okay, all right. Okay. I'm going to start over again. Sorry. I may just have to stop more often so that I don't have to re-record everything always. Okay. Wonderful. So let's get started. So the first thing that I would like to do is, if we're going to, because this is the first video on the series of exercises, I would like to step back a little bit and then encourage you to have an attitude before you do any kind of parametric modeling whatsoever. I would like to invite you to think through the problem before you actually start implementing anything or dropping any component, because I have found that thinking through the problem and setting yourself a plan, both conceptually and maybe geometrically, if you will, setting yourself a plan of how do you actually plan to tackle the problem is typically very helpful. Whether if you end up pursuing that particular path or you actually detour because of your lack of experience or because you're still learning the tool, whatever, it's not important. But what's important is to think through the problem and to make sure that you have a good sense of what things you're working with and how you may achieve the solution that you want to achieve. So in this case, for example, we are trying to design a pearl necklace. And let's imagine that this is for some kind of visualization exercise. We're going to make a rendering out of this, okay? So one of the things that is super important and very useful is to first think, what are your input parameters going to be? What data are you going to start working with as in the origin, and then which data you're going to have as input parameters to work through in your algorithmic process. Typically, for example, if we're designing a pearl necklace, one of the inputs might be the actual thread of the necklace, okay? And another input may actually be, for example, the amount of pearls that we might have. So for example, that's going to be, I'm going to call that n, all right? So that could be one parameter. I could choose how much is that, and that could vary. That could be 10, 12, that could be a slider, it doesn't matter. But it will be one of our input parameters, the things that we decide to change, right? Now, my question here would be, can we also choose the diameter of the pearl? Is that a possibility? Well, it turns out that if I have this length, if I have this curve that I know that I have in Rhino that I have generated parametrically, and I know how many pearls I want to put in that thread, then it turns out that I don't have the freedom to choose the diameter of the necklace, of the pearls. I don't have that freedom because it turns out that, imagining that they're going to be next to each other, right? Then an approximation to the size of those pearls will be that the diameter of those pearls should then be roughly equal to the overall length of the curve, so that would be L, divided by the actual amount of pearls that we have. So that's going to be n. So it turns out that d is not a free variable that you can use, that I can use in my definition. It's not a parameter. It's going to be parametrically bound to two things that are parameters to me: the curve, and therefore its length, and the amount of pearls that I have, like here. All right. So you see, so now breaking this up starts giving me some insights on what I can choose and what I cannot. And now, how do I go about this? Well, maybe, for example, one thing that I could do to generate this would be, if I have this curve, maybe I can do a process where I can divide this curve in equal length segments. How many? Well, equal to the amount of pearls that I want in my necklace. All right. And then once I have that, I can calculate the diameter of the spheres, and then I can just place spheres with that diameter centered on each one of those points. All right. And if I do that, then that could be a good start for my parametrically defined pearl necklace. Okay. So this is going to be super easy to implement. Let's go back to Grasshopper and take a look at how to do this. Okie dokie. Right, so that went much better. Please remind me, I'm going to forget about this. Please remind me that I need to, when I finish this video, I need to record the introduction where I say, hey, this is an exercise we're going to do, blah, 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 etc., etc. Okay, please remind me of that. So let's go back here. And the sun is starting to hit. Wait, so let me close the window. Let me close the window, and then I'm actually going to open the window, the other one, because it's kind of warm in here. All right. How's the lighting? You can still see me correct, right? What if I turn this on? No, I don't like that. This is a bit more natural. All right. So back in Grasshopper, this is going to be a piece of cake. So you'll see. First of all, we want to have the curve. We want to have the curve that is going to be the thread. So we could generate that parametrically. But as I said in previous videos, for some things, it's actually much nicer to have the tangibility, to be able to touch and move things around in Rhino, more than like moving sliders, whatever. So I'm actually going to just draw a curve here in Rhino. So for example, this is going to be the curve that I'm going to use as an input for my definition. And it's going to be, I'm actually going to make it like 3D. So I'm going to give it some volume here and some volume here, so that it's not entirely planar. And I'm going to double click here, type curve, right click, set one curve here, and then I'm going to just place some bifocals here for those of you who might be not icon people, which I think you should rethink your icon life, but whatever. I embrace all kinds of visual representations. So I have the curve, and remember that when doing exercises and modeling, it's very, very useful to have a panel always handy so that you can keep plugging things in and see visually what's happening inside the components. I have the one curve, okay? So that's going to be one of my inputs. The other input is going to be the number of pearls. So for that, I'm just going to use a slider that I'm going to right click, edit. I'm going to make sure that it's an integer because I don't want to have 2.3 pearls. That doesn't really make much sense. So I cannot have decimal part. The minimum is going to be number 2 because I don't want to have less than 2 pearls. And the maximum can be whatever, 1,000. It doesn't really matter. Okay? And then I'm just going to crank this up, for example, to the value of 10. So this is going to be the number of pearls, for example. And you know how I like a lot to have all my inputs grouped here on the left hand side. This is called inputs. Okay, and then have everything cleared. I'm going to just keep 100 here so that it's a bit easier to move this around. Okay, wonderful. So what is the next thing that I need to do? First, as I showed in my diagram, I need to subdivide my curve in an amount of points, which is equal to how many pearls do I have. So in order to do that, how do I subdivide a curve? Well, this is something you're going to have to start doing your own, which is going through the library of components and then just figuring out, reading through components and finding the ones that might help you do certain operations. So if I want to subdivide a curve into points, I wonder if components to do this would be either in the curves family or in the points family. I probably want to go to the curves family, and you can see that there's a whole category called divisions here that gives you many options to do different divisions for curves. And if I say divide curve into equal length segments, I think this is one that is probably going to give us good results. As usual, the first thing that we do whenever we drop a new component that we have never seen before is take a look at the inputs and the outputs. The input is the curve that I want to divide, how many numbers of segments I'm going to be dividing in, and whether if I want to split at the kinks or not. I'm not sure what that means, but I can still try with. And then this is going to be the division points. This is going to be the tangent vectors at dot division, which I don't think I'm going to be using, but it's okay to have. And T is going to be the parameter values at the division points. Remember when we spoke about Nernst geometry, we spoke about the parameter being that relative position that we can situate ourselves along curves inside of the domain of the curve. So T is going to be that value for each one of these points. So I'm just going to plug in here the curve, and I'm going to plug in here the number of pearls. Actually, if you read carefully, it says here the number of segments that I want to divide, and here I am saying the number of pearls. So if I actually crank this down to 2 segments, you see that I actually get 3 points. It's not exact, okay? It's not perfect. So this should be more like number of segments, but just doesn't really make sense. So we could actually say, well, maybe to be more precise, what I want is, if I want 3 pearls, what I need is to divide in 2 segments. So what I will need to do is, and I'm going to use an expression here, I will need to take whatever you give me minus 1. Remember that I just happen to like expressions better for computation, you see? And now this is going to be much, much cleaner. Remember to read carefully always the expression. This is number of segments, not the number of pearls. So now I have number of pearls is going to be 10, and now I have exactly 10 pearls here. And then the only thing that I need to do now is I just need to place on top of these, I need to place spheres, which I can find under surfaces, primitives, spheres. I can place spheres on the points, and let me see the points here. Yes, so all the points from the divide curve, you can see that I have a collection of 10 points, which are also the ones that I can see if I click here, I can see the 10 points. If I use those 10 points as the centers for the spheres, you can see that now I have the pearls, right? And that if I can increase more or less, and I can have more or less pearls on my necklace, which is kind of nice, right? However, the problem is that the radius for these pearls is always 1, because that's the default in the component. So, as we saw before on our diagram, it turns out that in order to make this happen, correctly, what we need to do is we need to calculate the diameter of each one of the pearls dynamically. We need to calculate it parametrically using data in our definition. So how do we do that? So I'm going to create another expression. You know how I like expressions better than than normal operators. And what we're going to do here is I'm going to say n is going to be the number of inputs. And then L, capital L, is going to be the length of the curve. And if you remember from our diagram before, oops, oh, sorry, I didn't change my screen. So if you remember here, from this diagram, we have the diameter is going to be equal to the length divided by the number of pearls. So if I now create an expression component and I replace, let me do that again. I'm going to create expression component, and this is going to be the length of the curve, and this is going to be the number of pearls. All right? So now what I need to do here is that the diameter is going to be L divided by N. And I need to plug in here the number of pearls, so that's going to be N. And you might feel inclined to connect the curve here. But that is not going to work, right? Because it turns out that the curve, you cannot plug here on L something that is expecting a number to work with. You cannot plug in a curve. The expression component cannot automatically decide that if you give it a curve, what you're actually meaning is the length of that curve. So what you need to do first is, using some kind of calculation, figure out the length of that curve. Thankfully, Grasshopper gives us components that can do that very easily. So for example, if I go to curve, you can see there is a full tab called analysis that can give us information, a lot of information about curves in general. One of them here is the length of a curve. So it literally takes a curve and it measures the length. If I place that here, the input component is the curve you want to measure, and L is the length of that curve as a number. So I can just plug that in here. Let me use a panel to make sure that this is working well. Yes, the length is 89 units of whatever. And then here, I'm just going to place that here under L. Now, it turns out that the result is that each one of these is 4 units long, 4 units in diameter. So if I plug this in here, you can see that now, we're getting close, but not quite. What is going on? If I go to the top view, you can see that actually, most of the spheres are actually overlapping with the center of the other spheres. You see that? That is because what I have calculated here is the diameter, but what the sphere component is asking me is for the radius. You see? So it's very important, as I said before, to always read the inputs carefully so that we know what to do. So how can we calculate the radius then? Well, the radius is just half the diameter, right? So I can change the expression, and say I want to divide length by 2 times n, or whatever the result of this was, I just want to multiply it by 0.5. Both of them work well, okay? And if I do that, now you can see that the necklace, the pearls are fitting well with each other. And look at this, is the nicest thing. If I increase the number, you can see how the diameter is slowly decreasing because they're parametrically related. Whereas if I increase the number, then you see that everything adjusts accordingly. And if I change now, if I move one of the points of the curve, and if I stretch the curve a lot, you see how all the pearls just increase in size to adapt to the new geometry. Okay? So literally, this is the magic of parametric modeling, just by making sure that we have the right information and that everything is parametrically related to each other. Then we can create complex relationships of modeling form between different geometry types. Now, a quick footprint to this exercise. I have taken many shortcuts here because, for example, if you actually look carefully at what's going on here, you cannot really calculate the diameter of the necklace just by subdividing the length because if you look carefully, you can see that sometimes you're going to get this situation where the curvature is very pronounced, the necklaces and the pearls are overlapping, whereas when it's not, then you're going to have a gap between them. And similarly here, you have some overlaps, and here you have some gaps. This is because the process that we have followed does not really take into consideration perfect tangency, okay? And that in order to do that, we would have to use other components here, like for example, divide distance, and follow a different logic. So this was just for the sake of oversimplifying the process. But if you actually want to see how this works, we have an algorithmic modeling challenge on pearl necklaces, which is somewhere here. This one. If you're actually interested in that, make sure you check our algorithmic modeling challenge 3.1, 3.2, where do we improve that and we make things perfectly tangent. And if you are maybe at that point in your life, you can see the exact same implementation using C#, which you got here. So that was it. Thank you very much. And let's move on to the next exercise in this series. And if you like this, like the video, maybe subscribe. I don't know. Thank you. See you in the next video. All right. I need to record the introduction. And this is going to be exercise 1, pearl necklace. Okay. And it's going to be E1, yes. Hello, this is Jose Luis, and welcome to this new video where I'm going to teach you how to model a parametric. Starting over again. Hi, this is Jose Luis, and welcome to this new video where I'm going to teach you how to model a parametric pearl necklace. And what does that mean? It means that starting off from the shape of some curve and then adding as one of the parameters the amount of pearls in a necklace, we're going to create a definition that is going to generate and populate an amount of pearls equal to whatever number we choose parametrically on top of that geometry. This could be used for visualization, it could be used for jewelry design, it could be used for many things. But the idea is that we're going to learn how to model geometry that is bound numerically to each other based on the relationships of the elements in this modeling environment. I'm also going to take this chance, that is the first exercise on this series, to take a closer look at how do we in general plan exercises and how do we plan our algorithmic modeling whatever we want to do parametrically. Okay, so shall we get hands-on? Let's take a look at that. All right. Okay, so we're done with this one. Woohoo! All right, we're going to save that. I'm going to save this. I'm going to save this without that. And we can probably keep that. And I'm just going to group this here. And there you go. All right, what is the next thing we are going to do? We're going to model a drinking glass. So, yes, so as we had it here, third point. Okay. To the coordinates. Okay, we're going to look at a drinking glass. Yes. Okie dokie. So we're going to start a new exercise. And then here. Okay, so the second one is going to be a drinking glass. And then here we're going to save this. And then we're going to start a new one. Okay. Where is my pen? What am I going to draw here? So I'm going to start by doing the drinking glass. Let's get busy. So as I said before in my previous video, the best way to start any parametric modeling exercise or work is to break down the problem into the steps that we think we're going to pursue in order to complete the exercise, and also think about what are the inputs between what are the inputs that we're going to be using and what is the relationship between them. So what I want to do is I want to, in general, get some kind of shape that is going to look something like this. It's going to be a base. It's going to be a drinking glass. all right? And if that's what I want to get to, I think that in general, a good way to get to this form will be perhaps to first model something that looks like the profile of the vase, something like this, and then by a simple process of revolution, if I revolve that shape in 360 degrees, I can probably get the surface that generates that drinking vase, that drinking glass, right? So then the problem is reduced to figuring out how to create parametrically the shape of the glass, the profile. Okay? If that's the case, then I can think of a few things that we can take a look at. So that we can use as inputs. So for example, first of all, probably the input that I want for this glass is going to be this point here. I want to start from the center of the glass, okay? The center of the bottom. Then something that I will want to also have control over might be the radius of the base. So I may want to have control of this distance, and therefore there might be another point here, and this is going to be the radius of the base. I'm going to call this capital R, the radius. And then this could have some kind of other point here, a third point, all right? And then this point could be the point that closes the polyline that becomes the curve that I want to revolve. And then there would be an axis here that I would do the revolution over. My question here would be, what parameters am I going to use to control where this point is in 3D space? You could argue, well, maybe I can use this radius here. But I would argue that perhaps that is not very intuitive, because if I do that, if I have, let's say, one slider for the radius on the bottom and another slider for the radius on the top, if I have two sliders, then maybe what would happen is that as I increase this radius, I would start getting a shape something like this, which would basically kind of break the inclination that I have already achieved in my glass. So from a design perspective, I don't think I would want to do that. So another thing that I could choose is, well, maybe I want to control this angle here, and that's going to be the parameter. And then I want to control that angle and maybe this distance here, inclined. Turns out that I, as a human, personally, I have a rough time getting a sense of how much 72 degrees is, and also having a rough time about like how much an inclined distance is. I'm much better at vertical distances and I'm much better at horizontal distances. So what I'm going to do, and this is my choice as a computational designer, there's no right or wrong here, and it depends on many aspects. What I'm going to choose is to, in my case, I'm going to choose to use this other distance, so from here to there, so I'm going to call this B. I'm going to choose that additional distance to be what I control about the point, and then this vertical distance, H, to be what I control about the other point. So that if at some point I have decided that I like a particular height and a particular distance that generates an inclination of the base, then anytime I change the radius will get larger, but the inclination will remain the same. And therefore, I will have a better control over the parametric relationships of this base. Again, this is just me as a designer, and I choosing what do I want to control. There is no right or wrong here, and we can all have an opinion on which maybe you think that a different application is better. Or maybe if you are designing this for the perfect stacking and packing, whatever, and some kind of optimization, then maybe you want to choose the angle. It's up to you, okay? So I think for me, the radius, the horizontal inclination, and the height are going to be the parameters that I'm going to use to model this face, okay? And then the process is going to be as simple as first, and also the center of the class. So I'm going to take this center, that's going to be an input parameter, and then I'm going to calculate, if this is 0.0, I'm going to calculate 0.1, and then I'm going to calculate 0.2 based on the relation of this point and these other three parameters. I'm going to trace a polyline, and then I'm going to revolve that in 360 degrees. And that's going to be my my drinking glass. It's going to be super simple. Okay, let's take a look at how to do that with actual code in Grasshopper. Alrighty, Bartulhokumu. Thank you. I didn't forget. What I forgot actually was to do an exercise, to do a video that I wanted to do on nerve surfaces. I actually have to go back and do that. I forgot to do that. Yes. Okie dokie. So back to Grasshopper. Okay. So I'm going to do Where am I going to start? Am I going to start with the point in Rhino? I'm going to start with the point in Rhino with that for this. Let's get started. The first thing that we said we wanted to use as input parameters was going to be the center of the class. Remember that that is a point. So remember that there's two ways we can go about this. One is we can just generate the point with X, Y, Z coordinates in Grasshopper, or we can create a physical point in Rhino and then bring it into Grasshopper. So for the sake of explaining some other techniques, I'm actually going to do that. I'm just going to place a point here. I'm going to right click here, take point, and then just right click and set one point and input that here. And for those of you who don't use icons, I'm just going to place here bifocals. Okay, so I have this point here, and which is going to be the center of the class. And then I'm going to add a few more parameters. So I'm going to add a new parameter that is going to be a slider, and it's going to be, I'm going to call this capital R. And remember, as per our diagram, that's going to be the radius of the base of the class. So this is going to be a slider that is going to go from 0 to, for example, 10 units, for example. And I'm going to set this at the value of 1 right now. So that's going to be one parameter. Then the next parameter that I'm going to throw in is going to be another slider. And that slider is going to be lowercase b, which is going to be the horizontal offset from this point to this point, how far they are away horizontally. Okay, the way I'm going to do that is I'm just going to right click here and say B, and then I'm going to edit this, and I'm going to say, well, this is going to be from -5 because it could go inwards. Maybe we want to design a glass that can bend inwards, but if we don't, we can actually cap that possibility by just saying that the minimum of this slider is going to be 0. And then the maximum is going to be +5, for example. And I'm going to leave it at the value of 0.25. That's good with me. And then I'm going to just copy paste this one and then say that this slider now is going to be h, and it's going to be the height of the class from 0 to 10, just like the previous slider. I'm going to align things up, group things, whatever, and now I have my inputs. Correct. So this is great. So now I am ready. These are the inputs that I want to use for my definition. And now the only thing that I need to do is I need to find, I already have point number 0, the one at the center. I need to find point number 1 and point number 2. How do I do that? Well, turns out that the relation between the 3 points in terms of coordinates is actually very clear, because if you think about this, if this point has x, y, and z coordinates, whatever those are, If we think that this vase, this glass is something like this, so this is X and Y and Z, it turns out that whatever this point is, this point is going to have the X coordinate of this point is going to be whatever the X coordinate of the point at the center was, plus the radius, correct? And then the other two coordinates, Y and Z, are going to be the same. So in order to find point number 1, the only thing that I need to do is I need to figure out these coordinates and create a new point where the X coordinate has the radius added to it. So let's just do that. So how do I go now about, I have the point that has been referenced here, and I can see that that point, I can't really read the coordinates here, but it has whatever X, Y, Z coordinates. How can I read those coordinates, the X, Y, Z, and then add some number R to the X? Well, it's actually quite easy. So if I go to the vector tab, and if I go to point, you can see that we have used the construct point. Given 3 numbers, I can create a point object. But it turns out that there's the exact inverse component. Given a point, give me the 3 numbers that define their coordinates. So I'm going to place this one, deconstruct, takes a point here, and now I can see the X value, the Y value, and the Z value. All right, so then point number 1 is just going to be as easy as saying, I'm going to add to the X coordinate, I'm going to add the radius. And now I'm going to create a new point that is going to be the X coordinate is going to be the X coordinate of the previous one plus the radius. And then the Y coordinate is going to be the same, and the Z coordinate is going to be the same. You see what's happening here? And now, no matter where I move the original point, the other second point follows parametrically. And if I increase the radius, you can see that the other point is just always bound. So this is going to be, I'm going to call this point 1. Okay? How about that? I know that I've always said that I like expression components better, but I mean, I also use operator components here and there. Okay, there's nothing written in stone here in parametric modeling. Now the thing that I need to do is I need to find the point number 2, the one on the top. And then if I think about it, it turns out that the coordinates of this point X are going to be whatever the X coordinate of point number 1 plus B. And then, so because whatever these coordinates are plus this distance. Now the Y coordinate is going to be the same as in Y1, because remember, there is no depth here. It's not going anywhere deep. But the Z coordinate is going to be whatever the Z coordinate of number 1 was plus the height, so this value here. So the only thing that we need to do is now break down those relationships, take the coordinates of point 1 and use those to generate point number 2. So let's do that then. So I'm going to go back here and say, I have the coordinates, I have point 1 here. So I could either say, well, I'm going to deconstruct this point again, X, Y, Z, and I'm going to operate with this. Or I could, if I wanted to be a little bit more optimal, just fetch them directly from here. I know that this is the coordinate of X1, and I know that these are the coordinates of Y1 and Z1, because that's what I'm using here. But for the sake of visual, I'm just going to do this. It's not the most optimal. I'm doing extra operations, but it's fine. So I'm going to take this, the coordinate of 1, and for X, I'm going to say, I'm going to add B. Y is going to be the same. And for Z, I'm going to add the Z coordinate, I'm going to add the height. And then now, I'm going to construct a point with the new X, the same y, and a new z. And if you look at that, and if you look at this is going to be point number 2. Let's see if this works. I can increase the radius a lot. If I increase the radius, and you can see how the whole wall moves accordingly. I can do negative and positive, and I can increase the height here a lot. So let's do this a little bigger. So this is going to be this, and this is going to be the radius. Okay, and then I have the 3 points now. I have first point, second point, and third point. Can I join those with a polyline? So let's do that. So I'm going to type here polyline, and I'm going to add the first point, the second point with the shift, and the third point with the shift. And now I have created the wall for my drinking glass. And I'm going to give it a little bit more of an inclination. Okie dokie. Wonderful. So we have now the wall. Now the only thing that we need to do is we just need to create a vertical axis, and we need to revolve this curve around that axis to generate a surface of revolution. How can we do that? If we go here to the surface tab, and if we go to freeform, you can see that somewhere, where is it? Revolution. We can create a surface of revolution. Let's drop this and see what parameters does it need. So I'm going to need a profile curve. I'm going to need a revolution axis, and you can see that the icon tells me that it has to be a line. And then this is asking me the domain of the revolution. So from 0, and you can see that by default I have from 0 to 2 pi. 2 pi in radians is 360 degrees. Okie dokie. So let's take that. I'm going to fit here the curve. And then for the revolution axis, I actually need a line. Okay, so turns out that, do I have a line? Do I have anywhere this line, the line that I need to use in order to revolve the surface? I don't have it. So I may, just for the sake of temporary geometry, I may need to generate that so that I can feed that data to the component. How am I going to do that? Well, I can just generate a line that is going to be this point, and between that point and another point that is any distance on top of it. It doesn't really matter. So what I'm going to do is I'm going to take, for example, I'm going to take this component. I'm going to take this point. I'm going to deconstruct it here to the z-axis, to the z-coordinate. I'm just going to add some random number. So I'm going to create a panel, and I'm going to just use 1 as an unit. This is not even going to be a slider, because I don't want to have the user think that this is something that they should, oh, sorry, I'm not sharing, sorry. So I'm going to take the original point, I'm going to deconstruct it in coordinates, I'm going to add the z height. To the z height, I'm going to add 1 unit, and then I'm going to construct another point based on the same x, the same y, but a z coordinate that is a little higher. Okay? And then what I'm going to do is I'm going to create a line object between the second point that I generated and the first point, the original one. So now you can see that I have this line that is a vertical axis, and no matter where I move my point, all the other 4 points are parametrically linked to it, which is kind of nice. So I'm going to use this line as the revolution axis, and ta-da! Woohoo! What do we have here? Oh my god, it looks like a drinking glass, but I don't like the proportions here. Wait. So let me make this a little more and a little more slender. I kind of like this. What about this? This is looking kind of nice. Do I like this? I don't know. Let me see. I'm going to bake this so that I can see a little better. Okay, and I'm going to choose ghosted so that I can see. Let me try another one. So I'm going to move the point here. I'm going to bake, and I'm going to make a version of this that is going to be a little wider, perhaps a little more ample, and a little thinner. Okay, so I'm going to bake that one, take a look at it, and then I'm just going to copy another one. And now I'm going to make, well, maybe this could be a plate instead. If I just make it like very, very shallow. Wait, interesting. So it could be a glass, but it could also be a plate. Wait, and then I'm just going to bake this and boom. And this that you're seeing here is what's very nice about parametric modeling. The idea that by creating the tree of relationships that define a particular family of forms, then by modifying the input parameters, like where the glass is the center of the glass, and some numbers that define its parameters, its height, the width, etc., then I can explore the family of possibilities that this gives me, okay, in a parametric way. So in this exercise, we have seen how to generate something that looks like a drinking glass, or maybe actually even a plate, okay? And one thing that I would like to notice is that when I created this point and when I created this line, since this was kind of temporary geometry that I needed just for the process, but it wasn't really meaningful in my definition, maybe something that I want to do is just, I want to hide it. So I'm pressing Ctrl Q to disable the visualization so that in terms of the model, it doesn't obstrude what I'm seeing as the process. Just something to think of to keep your definition a little cleaner. Okay, you could also choose to just delete everything else, all the points, all the polylines, and then just keep it like super simple. You know, I don't know, up to you. All right. Okay, so with this, I think that was a good exercise, and now you can just use your glass generating algorithmic definition to generate a whole variety of these elements, bake them, render them, 3D print them, or whatever you want. Okay, let's take a look at more exercises. All right, I'll see you in the next video, and in the meantime, if you like what you saw, maybe like the video, subscribe to the channel, etc. Thanks a lot, and see you in the next video. Okay, and the introduction. I don't want to forget the introduction. Maybe instead of the B, can there be an H and a direct relation between R and the top R if the base changes automatically updates? For example, top R is 1.25, the base R. Well, that can be nylon, but then what I would say is that 1.25, I wouldn't want that to be a fixed number. I would want that to be a slider so that I can choose 1.25 and then there's always a proportion. Oh, but I can choose, oh, that is too much. Then I'm going to choose another proportion, etc. But that is indeed an alternative, and it's up to you as a designer. Which parameters do you choose to incorporate in your definitions? Okay. All right, so let me move this somewhere out of the way. All right. Good night, Chandra. Have a good one. And what is it going to be called? Exercise 2, class. Hi, This is Jose Luis, and welcome to a new exercise in this series of Introduction to Parametric Modeling, where I'm going to teach you how to model a very simple drinking glass, okay? But the beauty of this is that it's going to be fully parametric, so we're going to be able to choose, for example, the point of where the center is going to be, but at the same time, we're going to be able to choose a few other parameters, such as, for example, the radius of the base, how tall or how short the glass is going to be, and the inclination of this glass. And by doing this, we will be able to choose and explore all the variability of different forms so that we can then generate different versions, bake them, and then send them for rendering, for fabrication, for production, whatever you want, okay? Now, this is going to be a super simple exercise. We're going to learn the basics of numerical relationships between point coordinates. It's going to be super interesting. And yeah, let's get busy. Let's get doing it. Let's get hands on. Okie dokie. All right, so that is great. Then I'm going to group this and say revolution axis, and this is going to be the surface. Okie dokie. So we have that. Do I need to save this? I probably don't. Well, for the point, I may want to have the point there. Fine, I'll save it. Okay, so okay. All right, I forgot to record nerves surfaces. So I need to go back and do this one before we go into flower base, which I think that's where I'm going to. I think that's where I'm going to stop today. Yes, because chess pawn, I don't think I'm going to do it because it's just similar to the same ones before. But I want to do the chessboard, and I want to do attraction and repulsion, and the hanging cloth. So that's going to be nice. So, okie dokie. And I need to do that before 5 because I have meetings at 5 and 6 and 7. Oof. Oi, how's everyone holding on? Nylan. Well, I mean, it's a matter of choices. Again, when it comes to design and parameters, we all have our different opinions, and there's no right or wrong. Okay, so it's up to you. It's absolutely up to you. Okay. All right. So, okie dokie. Surfaces. Let's take a look. So I'm going to save everything beforehand. I'm going to save this. I'm going to close here. I'm going to save this and close. And I'm going to save this and close. And surfaces. I think for this one, I don't want to explain everything. I'm just going to oops. Okay. Oh, where are... Okay. I did have a file somewhere with a bunch of different surfaces. Where did I have this? Mm. Mm. I don't want to... Sorry, I'm looking through my files. See if I can just pull up an example of different surfaces. And I cannot. Where are those files? Where are those files? Here. I got it. I got it. I found it. uh, Okay. So it's going to be 7. Okay. So that's going to be here. That's going to be what? That's going to be 4.5. Nerves, surfaces. And that's going to be this one here. And that's going to be this one. Okay. Then color. And then okay, and then rule surface. And that's going to be here, and that's going to be, and that's going to be a set. Okay. And have I shown how to do surfaces before? Yes, we did it with the lofting on the exercise previously. One way. Nice echo new research oriented Joe, just learning from your streams. Okay, thank you. One way. You're more than welcome to join our Discord and give us suggestions on new topics. Oh, I forgot to mention we have a running poll here. If you go to topic suggestions and if you go to pin topics, we have a running poll on topics that you may want to see soon happening in Parametric Camp. So you're welcome to vote. Which icon are you interested in? Just click on the icon, click on the emoji that you think you want to see. Okay, I'm very dense today. I can't talk much more. All right, I'm going to record the tutorials and then I'm just going to call it a day. Is it a day for a run? Should I go out for a run? I think it's a really, really nice weather out there. Might be a good day for a long run, actually. Okay. Hi, this is Jose Luis, and before we go into hands-on trying things out, I also wanted to do a quick round of review on the different ways we have for modeling surfaces in general. And this applies to nerve surfaces, but it also applies to other kinds of surfaces. The idea is that, as I explained before, nerve surfaces are driven by control points, but very often, like only in very niche cases, do we actually generate these surfaces by designing the control points one at a time. Typically what we do is, in order to generate these surfaces, we start off from other parameters or we use like simple curves and we follow other processes to generate this form. So, for example, I'm going to run you by a bunch of these examples. And at this point, what I would like you to think is that you might just want to give it a chance to browse through the library of components that are available in Grasshopper, for example, or in Rhino, and take a look at, by reading these components and their descriptions, to see if you can actually figure out what they do. Because you will find, if you are familiar in general with 3D modeling, you might find that many of these operations are actually quite familiar to you. So for example, I have here a bunch of geometry that I have generated in Rhino. And remember that all the sample files that we use in this video series, in these tutorials, can be found on the GitHub repository that is linked on the description of this video. So I have here a family of curves and points that I'm going to be using for this definition that I have here, which showcases a bunch of different ways of creating surfaces. So for example, we can create, and if I'm going to drop here bifocals, we can create a 4-point surface by inputting the 4 corners of that surface. So if I take these 4 points and I feed them into a 4-point surface, we can see that we get, as a result, this kind of hyperbolic paraboloid kind of situation. However, if instead I take 4 boundary curves with any particular shape, and then what I do is I create an edge surface, what you will see is that Rhino will try to fit a surface to the boundary of the 4 curves that we have defined here. Obviously, it helps a lot if the 4 curves are ordered properly, and if their edges match each other, and if the endpoints also match. That is super helpful as well. You can find those here under 4-point surface or under edge surface. There is also piping. Piping is a very simple surface, which is basically a tube that is extruded along a nerve curve. So for example, here I have created 4 pipes that are boundaries to that original surface that I have created. So imagine that we had a structure that had pipes on the edges and it had this cloth or this tarp tensioning between them, for example. The fact that that I said is actually not technically right, because a 4-edge surface will probably not have the exact same shape as a tensioned fabric. Okay, so forget what I just said. This was a really bad example. Now, if I go down here, you can see that, for example, I can have two profile curves and I can do a rule surface throughout them. Remember that a rule surface is going to be a surface that always is, that is the result of moving a line, a straight line, across a particular trajectory. In this case, using the two curves as the rails for the motion of this straight line. Rule surfaces are very interesting because, for example, they're really useful for creating when you create them with concrete, and you can create the framework. The framework can be created with straight elements, and it's a very nice thing. It makes creating these surfaces much easier in the physical world, for example. But also remember that ruled does not necessarily mean developable. They are two different concepts. Okay. Last, well, it's not last. I can have, for example, three curves here, and then what I can do is I can create a loft, which is basically a surface that is fitted throughout the three curves, so it's ensure that the surface is going to pass perfectly through the three curves. In a way, if you can think of lofting as a surface that is interpolated over a collection of curves. That's one way to think about it. And then, last but not least, we have sweeping. Sweeping is the operation where you can create a surface by moving one profile curve over another curve as if the other one was the rail on top of which this one is moving. So for example, this one would look something like this. You can see how this profile curve is kind of moving along the rail to generate this undulated surface. Okay. How this works and the mathematics behind each of them, it's kind of complicated at this point, but in general, you can see that any operation for creating surfaces that you might find in Rhino probably has a mirror in terms of a Grasshopper component, and vice versa. Okay, so in order to create complex surfaces, I highly recommend that you go to freeform or you go to primitives and you explore all the operations that you have, all the ways of creating different surfaces. Okay, this is very useful, and if you're doing freeform modeling, you will use a lot of this very often. Okay, wonderful. So I think we're ready for some hands-on exercises in the next video. Is that what's happening? Are we getting dirty? Alrighty, let's do it. Thanks a lot, and if you like these videos, click, subscribe, like. Thanks a lot. See you on the next video. All right, so that's going to be 4.5. Okay. And this is going to be E0. It's going to be 0 introduction to exercises. And this is going to be E1. Pearl necklace. E2 drinking glass. E3 flower vase. I think that's the last one that we're going to do today because I'm a little like, oh. Yes, we're going to save. Okay, we're going to save that. We're going to save this here. We're going to save this without the bifocals. We're going to save it. And then we're going to open the drinking glass. I'm going to remove this, guys, and I'm going to save as flower vase. And here, it's going to shut this down. And then here, and here, I'm going to explain the same concept. Okay, so I'm just going to, no, I'm just going to save this and create a new one. All right. And we're going to create a flower base. And let me load before I do any of this. Let me open. Okay. Okay, so, all right. So let's do the flower base. Okay, flower base. All right. So, if you remember, in our previous exercise, we did a drinking glass, which was very simply a center point and then two other points that we wanted to control for the curvature, if you will, of that glass. So if we're going to make a flower base, this exercise is going to be, technically, is going to be identical to the previous one. I just think it's very important, so that's why I want to reinforce the idea. But if you thought you had the last one under control, maybe you want to skip over this one, I don't know. But the idea is going to be very, very simple. What I want to do is I want to create some kind of flower base that looks something like this. So I start with an opening and then maybe it has some kind of smoother curvature like this, and it ends up also on some kind of shape here, on some kind of base here. And maybe this one is just going to be a little more complex, not it's going to be a little more complicated, not more complex, which means that basically what I'm going to be doing here is I'm going to be creating also a profile that is going to be a straight line in the base, but then the other profile, instead of being another straight line, is now going to be a spline, it's going to be a curve. And then very likely what I would like to do now here is control what the center of the point is. I would like to control the radius of the base, and then I would like to control the position of other points that are going to give me the shape of the curvature. So maybe there is a point here, maybe there is another point here, and maybe there is another point here. So by working with those 3 points, I can control the curvature of the profile of the base, and I can play with its how wide it is, how tall it is, etc., etc. So how are we going to do this then? Well, parameters are going to be just like we did before. We're going to have a point, which is going to be the center. Okay, I'm going to call this point number 0. Then I'm going to have another point that is going to be point number 1, which is going to be at a distance r. So that's going to be the radius. And then I'm going to have 3 other points, which I'm going to call point number 2, point number 3, and then point number 4. And then what I'm going to do now is, just like I did in the previous exercise, instead of controlling them, each one of them individually in relation to the center, what I would like to do is control them sequentially, so that whatever I do to this point, for example, affects what happens to the following points, to point 3 and point 4. Because I think, in my opinion, and again, this is my opinion, you may have a different opinion, in my opinion, that kind of relationship is much nicer for modeling because it allows you to fine tweak and to adjust things from the global to the local scale. That's kind of how I like doing things. So that's why what I'm going to do is I'm going to define 3 heights. So I'm going to define the height of point number 2. I'm going to define the height of point number 3, which is going to be not the total height, but how far away from point number 2 that point is going to be. And I'm going to define another height, which is going to be height number 4. And then for each one of them, I'm going to define as well, I'm going to define B2, which is going to be how far off point 2 is in relation to the previous one. Then I'm going to define B3, which is how far off point 3 is from point number 2. And also B4, which is how far off point number 4 is going to be from point number 3. Then I'm going to create a interpolated curve, and then I will revolve that over an axis and then generate that form. Okay, so conceptually it's going to be almost identical to what we did before. It's just going to be a little more tedious. It's going to have more steps, but it's going to be conceptually the same thing. So shall we give it a try? Let's give it a try. We are back in Rhino and Grasshopper, and for this exercise, because it's going to be very similar to the previous one, I'm actually going to do a little fast. So if you can't keep it up, just slow down the video, or otherwise just look at what I'm doing, because I think you're going to be able to reproduce this very simply. So I created a point here, and now I double click and I bring in an empty point parameter that I use to import that point into Grasshopper. And then I'm just going to drop here some bifocals so that those of you who don't use icons can also follow up with the video. Then I'm going to decompose, well, I'm going to set up my parameters. That's going to be a slider that is going to be the radius, and I'm actually going to do this offline and then I'll be back. So I'm going to create the parameters that I have defined in my diagram. Okay, so let me do that. So that's going to be radius, and that's going to be from 0 to 10. Okay, and then I'm going to copy this, and that's going to be H1, and that's going to be H2, and that's going to be H3, and then B1. I'm going to be B1, which is going to go from -3 to +3, for example, and it's going to be 1 unit, and it's going to be 1 unit, and then this is going to be B1, B2, and B3, for example, B2 and B1. Okay. Okay. So here we are. So we have the point, we have the radius of the base, and then we have the increment of each one of the points, B1, B2, and B3, and we have the heights of each one of the points, height 1, height 2, and height 3. I think I actually did the numbers wrong. I think here I said B2, B3, B4, and H2 there. So you're going to forgive me about that inconsistency. But yes, so now we have this, and then remember, the first thing we're going to do is the first point is going to be the first point is going to be where point 0 was, and then we're going to add the x coordinate, we're going to add the radius. So we're going to do that, and we're going to say I'm going to deconstruct this point, I'm going to take its coordinates, and then to these coordinates I'm going to add the radius to the x coordinate. So I'm going to do that, and then I'm going to construct a new point. So that's going to be this one, and this one. And for the radius, I'm going to open it up a little bit like this. Okie dokie. So that's going to be, and I like, please label everything. Okay, so that's going to be point 1. And then point 2 is going to be, again, I'm going to deconstruct the previous point. I do have the numbers here. I could plug it right away, but it's a little easier to read, I think, if we do it this way. So I'm going to deconstruct this, and I'm going to say, well, for as per the diagram, to x, I need to increase by b, and z needs to be increased by the height. So I'm going to say, okay, so I'm going to add to the x, I'm going to add b1, and then to the, I'm going to double click addition, and then to the C, I'm going to add the height. And then I'm going to construct a point with this coordinate, and this coordinate. Okie dokie. So that's going to be point number 2. All right. And then that's going to be that. I'm going to open up a little bit like here. And then I'm going to copy and paste the whole thing, which it's very dangerous. Okay, so I highly recommend you never do this because copy pasting is the devil. It always gives errors, or like it makes debugging things very difficult. So I'm just going to replug this one here. So I'm deconstructing the previous one now, and now I'm adding the new base to the X and the new height to here, and then I have the third point. The third point is going to be, I want to bring it negative a little bit, and the height is going to be short here, and then I'm going to do the same operation. I'm going to copy and paste all of this, and then this is going to be point number 4, and then the point that I want to deconstruct now is this one, and the base that I need to add is B3, and the height that I need to add is H4. Okay? And then I have my 4th point here. So I have my 4th point, and that point is going to be there. And then you can see that it looks like I have the profile kind of, but the radius is a little too much. Well, we can see that very soon. Okay, so what am I going to do? First of all, because in this case, my modeling is that I have here, I have a straight line. And here I have an interpolated curve. In this case, I cannot do both things at once because they're different kinds of geometry. So what I'm going to do is I'm going to first create a simple line between point 0 and point 1. So that's going to be, between point 0 and point 1. So that's going to be the line for the base. And then for the other points, I'm just going to join them with an interpolated curve. So I'm going to do to here, to curve, spline, interpolate, and I'm going to add the first point, then I'm going to shift press to add the second point, press shift to add the third point, and press shift to add the 4th point. All right, and then you can see that now I have the profile, which is an interpolated curve. Awesome. So now the only thing that I need to do is I need to do the revolution, just like I had before. So I click here, I place a revolution. The profile is going to be this one. The axis, remember that we need to generate. So I'm going to deconstruct the point here. I'm going to add to the Z coordinate. No, sorry, not this point. The one at the base here. So the one at the base, I'm going to deconstruct it. I'm going to add some number, for example, the value of 1. And this one doesn't need to be a parameter because it's just auxiliary geometry. I'm going to construct the point again with the same X, the same Y, and the C that is a little higher. I'm going to create a point, a line between those two. So that's going to be the base point and the new point that I just created. So this is going to be the axis of revolution. And then I'm going to plug this in here as the axis. All right. Wonderful. So it looks like it's working, right? So let me do a couple ticks. So I'm just going to, let me find a nicer base. So for example, the radius, and then I'm just going to decrease this height a little bit. And then I am going to, what am I going to do? Oh, look at this. How cool is this? Yoo-hoo! Look how by affecting 1, everything that comes after gets affected. And how by affecting the one in the bottom, everything also... Oh, this is pretty neat, right? I like this. Oh, sorry, my head is on the way. But I think we could be cool with this, except for one tiny detail. So, if you look at the situation closely, if I bake this now, and I take a closer look, what we can see is that actually the vase is empty in the bottom. There is no base. And depending on what we're doing for rendering, this may actually not be a good thing. That is because, and I'm going to delete this, the only thing that we have revolved is actually the interpolated curve here on the side, which was this component here. We have not revolved the line. Okay, so there's two things we can do. We could just copy paste the revolution component, and instead of revolving this curve, we could just revolve this line. And then here we would end up with a surface that is the base, you see, that base, and then another surface that is the profile. However, this is not very, very clean because basically we have two different surfaces. And if we want to move things around, etc., it's just not great. So what we can do actually is we can join the two curves, the straight line segment and the interpolated curve into one single curve that has these two segments. The way we can do that is by joining curves. So actually, I forget where that is here in utilities. If you click here, you can see that you have join curves. So I can place this component and then I can join the line with the interpolated curve. What that gives me is a planar curve that I can now plug into the revolution. And you can see how this turned darker. That's because now this is also a surface. And if I bake my vase, you can see that the whole thing is now has a top and that is open and a bottom that is closed. All right. Okay, so this is going to be the surface. And then should we have some fun and create some? All right, so let me go here and now create what? I'm going to create one that is a bit more slender, perhaps. So I'm going to switch up. Look what's happening here. I'm having this like kind of flute effect. I'm going to make like this really elegant thingy. So it's going to be this, and then this is going to be super slim, and it's going to be here, and the opening of the other one is going to be super thin. So I like that. It's kind of like very like. So I'm going to bake this, and maybe I can do a third one that is a bit more like shorter and more open wide. So I'm going to do this, and then I'm going to reduce the height here. Maybe this is a little too much. Maybe I want something like this. That's kind of cool, actually. I'm going to keep that one. And yes. And then I'm just going to move this all the way out here. Alrighty, so this was the generation of an algorithm. Remember, we are designing parametric algorithms. This was the generation of an algorithm to create parametric vases for flowers, for example. And with that, we have created the tree of relationship, which is starting to look like an spaghetti of trees, but nonetheless, it works. And it allows us to explore formally the generation of these vases, okay, which I think is kind of nice. So this was an exercise to try parametric flower vases. I hope you liked that. If you did, maybe you want to like the video and subscribe to the channel. And otherwise, you may continue to the next video in this series, Introduction to Parametric Modeling, where I think I'm going to keep doing more exercises. We're going to try a different thing on the next video. So stay tuned and see you on the next one. Bye-bye. Thank you. All right, and we need to record the intro. We need to record the intro video. Okay, so that's going to be okay, so that's going to be okay. So I'm going to move this here. Alrighty. So and this is going to be exercise 3. Wonderful. So hello, this is Jose Luis, and welcome to this new exercise video in the series Introduction to Parametric Modeling, where I'm going to extend on what we did in the previous video with the drinking glass, and it's going to be a very, very similar example. Technically, it's just going to be a little more complicated because it's going to be designing the shape of a flower vase. And this is just going to involve working a little bit more with the curvature of the surface, but the techniques of relating points to each other is going to be the exact same thing pretty much. So I'm going to have still the option of moving this at any point in x, y in the world coordinate system, and then I'm going to be able to play with the radius of the base and with the radius of other parts of the vase, and then play with the curvature and how this looks in 3D space. It's going to be super interesting, and it's going to allow me to create formal families of different parametric bases. So if you're interested in this, give it a try and check out this video. Otherwise, it's going to be very similar to the drinking glass. So you may want to just skip to the next video, perhaps, if you think you know what we're doing. Okay? All right, let's get hands-on. Okie dokie. All right, so I think with this, I am calling it a day today. It's been a lot of recording. Oh, my ears hurt. Ow. Do you folks have any questions, concerns, things you want to share, etc.? I may have a couple of minutes to hang out and chill with you. Saeed, thanks to you. Have a good day, man. I'm going to start shutting things down here. And what else? Nylan, thanks to you, sir. I'm very happy that you're here. I'm not sure if I've seen you before on the channel, but if you haven't, just join the Discord and introduce yourself and let us know who you are and why you're here and all those kind of wonderful things. Saeed is I know, it's almost night here as well. All right, so I think this is it. All right, it was a pleasure. Thanks everyone. I'll see you tomorrow. Remember, we're doing this all week long. So until we finish parametric modeling, we're doing this. This week it's happening. Parametric modeling, Grasshopper, done. We're moving on to other things. Okay. All right. Have a good one. Thank you. Bye.